Hi, I'm Sara Papi from Fondazione Bruno Kessler and University of Trento, Italy, and I will present the paper Does Simultaneous Speech Translation Need Simultaneous Models? A joint work with Marco Gaido, Matteo Negri and Marco Turchi. I will start with what does simultaneous mean? A simultaneous speech translator, or SimulST model, has to produce the output translation while it continues to receive the audio input. So the goal is generating high-quality translation in the shortest possible time, that is finding the best quality-latency trade-off. And how does a simultaneous speech translation system work? The quality-latency trade-off is managed by a decision policy that defines whether to wait for more input or to emit one or more target words. And how is a simultaneous speech translation system trained? In general, simultaneous speech translation systems are usually trained to simulate the test conditions, that is, with partial input available. The necessity to consider the same latency regime at training and test time implies that different models have to be trained to reach different latencies. And the benefit of having the same simultaneous train and test condition has been taken for granted but never proved. So we ask, does simultaneous speech translation really need simultaneous models? Then we analyze different training regimes to discover this. The first one is the simultaneous training, in which we have to mask feature out of frame when computing decoder attention. And this means that we have the same train and test simultaneous condition. And the offline training, in which the entire input is provided without masking when computing the encoder-decoder attention. This means that we have different train test simultaneous conditions because we have a testing simultaneous and training offline. But does this train-test mismatch really affect the performance? So I first describe the experimental settings, and in particular, which kind of decision policy we use in our paper, which kind of model architecture, training data, and evaluation metrics. First, the decision policy that we adopt is the weight K, that is the most popular one. And in weight K, the model waits for keywords before starting to generate. But how words are detected from speech? Because with how to as input, the number of words can be determined in two ways. With fixed word detection, in which we assume that each word has a fixed duration, in our case 280 milliseconds, and adaptive word detection, in which the number of words is directly detected from the speech, for example by using the CTC to determine word boundaries. But which value of key is selected? Because we have two types of key. The first one is the key train that is used in simultaneous training to mask feature frames. For example, if we have key train equals to 3, only the first 3 source words are considered in the encoder-decoder attention of the first target word, and so on. And the key test that is used in the simultaneous inference for both the simultaneous and the offline trained models. And its role is to determine how many words the model has to wait before starting the generation. We experimented with two types of architecture, the transformer architecture and the conformer, that is the current state-of-the-art architecture in speech translation, and is composed by a conformer encoder and a transformer decoder, and with different training data for English to German and English to Spanish language pairs. That is, we consider only must-see, and we consider must-see plus sequence-level knowledge distillation that is performed using a machine translation model to translate the transcript of the mass cinema, and using this translation together with the gold standard translation to train our model. And to evaluate the translation quality, we use Sacre Blue, and to evaluate latency, we adopted the length adaptive average lagging, that is an improved version of average lagging for speech, that also accounts for the case in which the prediction is longer compared to the reference, And we analyze both the computational unaware and aware metric. That is, the first one, the computational unaware, considers only the ideal time and the computation of the latency, while the second one, the computational aware, considers the current elapsed time. So that is, it considers also the computational time. Then we move to the results. First of all, we show the result of the transformer architecture on SimulST using the fixed word detection for the WK policy. And this graph, we represent latency in blue, that is quality. With the straight line in black, we represent the offline generation, the performance of the model, using beam search with beam equals to 5, while with the dashed straight line we represent the greedy prediction of the model. And each curve of this graph is a model trained using a different key train. For example, the curve in blue is the system trained in simultaneous with key train equals to 3. The red one is with key train equals to 5 and so on, and the black one is the offline model using simultaneous. Each point of the curve is represented by a key test. And we see that the offline trained model always outperforms the simultaneous trained one. Then we use the adaptive word detection, and we see again that the performance of the offline system is nearly on par. This means that the offline simultaneous pre-translation model performs better, but what if we change architecture? What if we train the model on more data? How does it perform compared to the state-of-the-art CAT architecture? And how is its performance in real time, that is considering the computational aware metrics? The first comparison we made is the transformers versus conformer to verify if the architecture matter. And first we see that the conformer outperforms the transformer as in the offline scenario, and we observe also that adaptive word detection is better than the fixed one. Then we experimented with the SimulST with the knowledge distillation data, and we see, and then we compare our performance, the performance of the offline system with the best performance of the system trained in simultaneous, to verify if our finding also holds in this condition. And we discovered that with knowledge distillation, that word detection is better than the fixed one, and also that the offline trained model still outperforms the simultaneous trained one. So we can see that the adaptive word detection is the best choice if we consider more competitive training strategies and architectures. Then we compare the performance of our offline system with the state-of-the-art system CAT, and we tried also the greedy performance of CAT instead of the original performance shown by the authors in their paper. And we adopt our best setting, that is using the conformer with adaptive word detection, and we also use the knowledge distilled data, but also the CAT is trained on knowledge distilled data, so we use the same set of data to perform this comparison. We see that with considering the computational unaware matrix, that is the ideal times, the offline system performs better only at medium-high latency. While if we consider the computational aware metric, we observe that the curve of our offline trained conformer shifts toward the left, and so we can conclude that with relapse time, the offline model is even closer at lower latency to the CAT state-of-the-art system. So we can conclude that the simultaneous training is not necessary, that the offline trained model is better than the simultaneous trained models if we consider the WK policy, and that already existing ST models can be used in simultaneous without any modification. And so it means also that only one model has to be trained and maintained to perform both the offline and the simultaneous tasks. and that the offline trained model also performs the state-of-the-art at medium high latency regime, especially if we consider the computationally aware metrics. And our code is available on GitHub, and thanks for your attention.